So we've thought about the force that a magnetic field applies to a charge. Now let's think about the charged particle trajectory. Trajectory in a B field. Okay? So let's set it up. Let's just draw, say, a uniform B field into the plane of the board. This, all the arrow tails flying away, and there it is, B. Uniform B field. The charged particle, we can start it right here. It has some charge Q, and let's give it a velocity, because we know we need a velocity to get anything to happen, to have any force at all. So it has a velocity to the right. Well, we can figure out the force that you're going to get. It's going to be V, fingers along V, cross B, turn them towards the B vectors, so the force is going to be up. So this is pretty similar actually to when you throw a ball in a gravitational field. You can give it a velocity this way, and then it has a force up or down, so it sort of follows a curve. Its path is deflected. It continues its motion this way. This velocity stays constant, but it's accelerated this way. It gains velocity that way. So here, the force due to the magnetic field is going to deflect the trajectory. I can actually show you that with a real charged beam. So this is an evacuated tube, and it puts a big negative potential on this electrode. So high that it actually boils, electrons come off the electrode. It makes just a beam of electrons. It also has some a little bit of background gas that ionizes to keep everything stable and doesn't charge up too much. But mostly you have electrons flying off this electrode, and most of them go straight to this metal plate, and that's the end of the story. But there's a little slit in the plate, so some of them get through and make a beam that keeps going. So you've got a beam of electrons, and this little plate is tilted a little bit, so they slowly, along this direction, they crash into the plate. The plate has a phosphor on it, so it lights up when they crash into the plate. So when I turn it on, there you can see the beam. That's a beam of electrons flying through the tube. So what we're going to do is bring a magnet and see what it does to the beam of electrons. Because remember, this bar magnet, the field lines go from the north pole, the red is the north pole, to the south pole. So if we just think about the poles, or the field right at the ends, because we're going to use the ends, it'll be this way near the north, it'll be pointing in the south. So I will bring the north pole pointing at me at the beam, and let's see what that'll be. We have the beam going this way, and I'm going to bring this pointing in, so we're going to have a B field like this. So V cross B also the same as this. It should be up. Right? So let's see what happens. There's our beam, and I bring in this magnet. Oh, there's the deflection we hoped for, but it's down. And it's down. And why is it down? It's down because they're electrons. Right? Q, in this case, equals negative E. The charge is negative. When the charge is negative, the force magnitude is negative, which means it goes the opposite direction. Right? So right-hand rule says it's up for positive, but the force is down for an electron. So it did deflect the right way. It deflected down. We can also check, we can take and aim the south pole at the beam. So here we go, bring in the south pole, and there it goes, it deflects up. Just like you'd expect, because when you bring in the south pole, the beam, or the magnetic field is pointing the opposite direction. Now I'm bringing in a field that's pointing away from the beam. So it would seem that the charged particle beam really is deflected the direction that you would expect. So let's see what kind of motion that will create. So if it's moving along in V, it's fine. And if it's just accelerating this way, it's kind of like a rock that you throw. Do something like that. Okay? But wait a minute. Now something changes. Now we made it to here. And now which way is velocity? Now velocity is that way. All right? V cross B, the force is now that way. So as our velocity changes, our force also changes. Okay? So you say, okay, well, it'll follow the trajectory like that. Oh, but wait a minute, when it gets to here, the velocity's changed again. Now the velocity is this way, and the force is now that way. Say, okay, it's going to kind of go like that. Well, you can see what it's going to do, and you've probably read already, you know what it's going to do. It's going to make a circle. And it's just going to go around in a perfect little circle. Because since magnetic force is always proportional to the velocity the charges move in a circle. And they follow all the laws of circular motion that you learned in mechanics. The reason these don't go in a circle is two reasons. One is for the field we're generating, the radius of the circle is really big, much bigger than the tube. And also, this magnet does not make a uniform field. It's just making a little local field right on the beam. It's just enough to deflect it. That's why we're just seeing a deflection. But in a large uniform field, those charges just go in a circle. Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put at a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. So you're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam if you bring in a strong, concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here we're going to start turning it up, and you can see it's starting to curve more and more. And right now it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. But if I keep turning it up, more and more current, bigger and bigger B field, eventually, there it is. It makes a circle. Perfect circular motion going right back to where it started. And if I turn the magnetic field back down to zero, straight again. So there's direct visualization of the circular motion of charge in a magnetic field. Let's analyze this circular motion a little bit. Let's say we're given a particle, mass m, charge q, in a uniform B. So again, let's put it in a uniform B that looks like this. They're fun to draw. And we already agreed that the charge will go in a circle because it'll always feel a force at right angles to its velocity. So it's going to go around like that. Going around this way, feeling a force, always seeking the center. So the first thing you could ask about this motion is, what is the radius? All right. Well, you get it by solving kinematics the same way you solve them for 1D motion, is you apply Newton's law. Sum of the forces equals ma. We can apply that here. Now we're not doing it quite as generally as a 1D problem in 3 dimensions. We're assuming we have circular motion. Since we're assuming circular motion, we know that what goes here is the centripetal acceleration. If you want to be general, you could have both translational and centripetal acceleration. But here, we're confined to a circle, so it's only that. So we can solve it and say, well, what is the force? Here we're just going to do magnitudes. We're not thinking about directions. The direction is constantly changing. The magnitude of the force is Q VB. All right, we were given Q, we were given B. We know it's moving with some V. And that's going to equal to M. We were given M, and the centripetal acceleration is V squared over R, which you may remember from mechanics. There's R, the radius of the circle. So we can start canceling things and see that and solve for r, and you get that r, the radius of the circle, is mv over qb. So that's worth memorizing, especially when you're taking a class in magnetism. The radius of the circle of a charged particle in a uniform field is mv over qb. It even rhymes, mv over qb. It kind of makes sense too if you look at it. This is the momentum of the particle, right? Mass times velocity. It kind of makes sense. The more momentum it has, the harder it is for the field to get it to turn. Right? So the bigger the momentum, the bigger the radius. That's why it's in the top. And qb are related to the force. The bigger q, the bigger the force. The bigger b, the bigger the force. The bigger the force, the bigger influence it has on the motion. So it's going to push it even harder. So therefore, the bigger q and b, the smaller the radius. So that one makes sense. The radius is mv over qb. We can use this same diagram to ask another question. What frequency? So as this particle flies around the loop, how fast? How many cycles does it go per second? So I want to take this opportunity to talk about frequency a little bit. So you're used to thinking of frequency perhaps as f. If you haven't had a lot of physics and a lot of math, frequency is f. It describes cycles per second. And the unit is hertz. That's frequency. That's the frequency we always talk about that we're used to thinking about. We get into physics and we like to use another frequency, omega. We use it to keep up usually with things either going around in a circle, where you might call it the angular velocity. We might use it to keep up with something oscillating up and down just in sinusoidal motion, call it the angular frequency. But we always use omega and not f. Okay? Here's one way to remember it. Frequency f is frequency is cycles per second. Omega is circles per second. Circles per second. What is that? What is a circle? Well, a circle, what's a circle? It's 360 degrees. Oh, but we don't use degrees either. Okay. A circle is 2 pi radians. Okay. So really then, omega we keep up with in radians per second. So if you grew up with hertz and you love hertz, you got to give it up. You got to switch to omega. They're the same thing. There's no difference. Okay. It's really just a factor of 2 pi. Omega in any experiment, any problem you're doing, is always 2 pi times f. Because if one cycle is a circle is 2 pi radians. So you just multiply your cycles by 2 pi and you get omega. Okay? So if you're not used to omega, get used to it, because we're going to be using it a lot. That's what we usually use in physics. Let's ask ourselves then, what is omega here? How do we get omega? In this case, if we can just sort of talk our way through it, we know it's going to depend on how fast it's going, right? It's going some speed v. And how many circles per second is that? Well, you take the speed, how many meters per second it is, say 10 meters per second, and you just divide by the circumference. Right? If it's 10 meters per second, the circumference is 2 meters, that'd be 5 circles per second. So we're going to divide by 2 pi r. Okay? That's circles per second. But we actually do it in radians per second, so we need to multiply those circles by 2 pi. And then you can see the 2 pi's go away. So omega is v over r for any circular motion, actually. So now we can say for this case, we plug in for r. We already solved for r in terms of all these variables. Remember, it was mv over qb. So it's in the bottom. So I wrote mv on the bottom, qb on the top, and that v is still there. But then look, those go away. Okay, so the omega we want, finally, the angular frequency of this thing, of the particle going around the magnetic field, is qb over m. And this is kind of fundamental and interesting because you find that the frequency it goes around has nothing to do with how fast it was going. It only depends on fundamental things to the problem. It depends on the charge of the particle, it depends on the mass of the particle, and it depends on the magnetic field you apply. So if I just take a big smattering of electrons and just throw them into a constant magnetic field, they're all just going to start spinning. And they're all, no matter what their initial velocity is, they're all going to just spin at the same rate, or at the same angular velocity. If I take a bunch of protons and throw them in, they're going to spin at a very different velocity, have a much bigger mass. If I take two kinds of particles and just throw them in the magnetic field, you can tell them apart because they have different ratios of charge to mass. Right? So that's one way to identify particles, is how fast do they spin. So since this frequency has sort of this fundamental property, it's called the cyclotron frequency. It doesn't depend on the details of the motion. It doesn't depend on the radius or how it got there or how fast it's going. It really just fundamentally depends on the particle. And you can speed it up or slow it down by adjusting the magnetic field. We've thought about circular motion kinematics in a magnetic field, so now let's do a problem. So this is going to be, if you're using Serway and Jewett 8th edition, this is chapter 29, problem 22. And if you're not, don't worry about it, because I'm going to tell you the problem anyway, so it doesn't matter. Okay, so in this problem, we have a region with a uniform magnetic field pointing into the board. So this is, remember how we always draw a field into the board like this. But the uniform field does not exist everywhere. It's only to this side, say, of this dashed line. So on a plane to the right, you've got a magnetic field pointing into the board. And to the left, the magnetic field is 0. Here, we're going to give it a value of 1 millitesla. The magnitude is 1 millitesla. Here, the magnitude is 0. Okay. So now, an electron is going to fly with an initial velocity, and it's going to hit this uniform region perpendicular. So it's flying perpendicular to this boundary of the board. And you know what's going to happen is when it goes into the magnetic field with some velocity, it's going to make a circular orbit. And you can kind of imagine it's going to come in, it's going to make a circle, and it's going to go out. So that's really the problem. So we're given the electron has an initial velocity, so we'll draw it here. Electron, initial velocity, and we're just given v. We're given numerically 1 millitesla for the field, but we're only given v for the velocity, whatever. So let's say it's going to come in, enter the region of the field. Let's calculate the force. It's going to be V, fingers along V, right-hand rule, cross with B. The force is going to be up. No, it's not going to be up. It's an electron. The charge of the electron is minus E. So when you put that in, the force is going to be down. So I drew this on the wrong side on purpose, of course. So I'm going to draw this up at the top. Because since the force is down, here's your electron. Has an initial velocity v. It's going to go in here. And yes, Q, let's see, v cross b would give you the force up, but since the electron charge is negative, flips the sign. The force is down. So since the force is down and the velocity is this way, it makes a semicircular path like that. And it comes out as an electron with that same velocity v once it gets out. So that's what we're given. Electron, velocity v, goes into 1 millitesla. The first question is A, how much time does it spend in the B field region, or just the B field? Basically, how long does this take? It looks like a tricky problem because we were given 1 millitesla, but we weren't given the velocity. We don't know how fast it's going, and we don't even know the radius. The radius would tell us how far it went. So how do you do kinematics? Well, when you know what to do, you just start writing down the equations that you know. Right? So the radius, we know, if we're in circular motion, we know that that radius is mv over qb. Okay, well, we don't know v, so that doesn't get us very far. But the other thing we know is that omega, the frequency, is qb over m. And this is the one that's going to help us, because remember, for the frequency around which the particle goes around a circle when it's going in just a circular motion, all it depends on is the magnitude of the magnetic field and the properties of the particle. The particle's mass, which we know because it's an electron, and the particle's charge, which we know because it's an electron. This is actually the one that we know. And omega is really what we want. Remember, omega is the angular frequency. How fast is it, how often does it go around? That's really the question. How long does it take to make the semicircle? So we don't really need to do the kinematics in terms of d equals vt. We really just need omega. So let's think about what omega is. This is a check mark, by the way. There you go. It's less confusing. Let's think about omega. What was omega? Omega is the grown-up physicist way to think about frequency, right? Omega is in radians per second. Now, we're used to thinking of frequency possibly in terms of hertz, in terms of f, cycles per second. Right? So remember, this is how you tell them apart. F is in cycles per second, or hertz. But remember, a cycle, when you're going in a circle, is 2 pi radians, right? Cycles per second, it's cycles per second, sort of. So if we're going this many cycles per second, and we're talking about circular motion, if you want to get it to radians, you just say, well, how many radians are in a circle? Well, 2 pi. Right? That's how you get from omega from f, what you're used to thinking about. Okay. F is related, the frequency is related to the number we need. We want to know how long does it take to go around the circle. Well, that's the period. That's what you know is the period. So we know that's 2 pi 1 over t, where big T is the period, and that's just in seconds. Okay. And we know this all is equal to QB over M. So if we wanted to solve it for just the period, then you would just turn this whole thing around, and what would it be? T would be, this would come over here, it would be 2 pi M over QB. That's how you get the period. So let's go ahead and start plugging in numbers, see what we get. Let's see, T, the period, is 2 pi. We know what those are. The mass is 9.1 times 10 to the minus 31 kilograms. And the charge is 1.6 times 10 to the minus 19 coulombs. And B was a millitesla. That's 10 to the minus 3 teslas. So if we do everything in MKS units, that's what we get. And therefore, the answer is going to come out in seconds, but I'm going to put nanoseconds. It comes out to 36 nanoseconds. That's not the answer. Right? That's the time it takes to go all the way around the circle. But our path is only halfway around the circle, because once we go halfway around, we come out of the field. Okay? So the real answer then that we want is simply half of that, 18 nanoseconds. So if the electron flies in, doesn't matter what its initial velocity is. It can be going really fast or really slow. It's going to go through here in 18 nanoseconds. All that matters is the properties of the electron and the magnetic field. If it's going really slow, then it'll just do that. If it's going really fast, it'll make a bigger circle, but it'll always take 18 nanoseconds. Second part of the question says it gets 2 centimeters into the field, into the B field. What is the kinetic energy? That's a strange question, it seems. We haven't even thought about kinetic energy. We don't know what's going on. Well, kinetic energy for a microscopic particle like an electron is the same as it is for a baseball. It's 1/2 mv squared. So we know the mass. All we really need is the velocity. We still don't have the velocity. We did the whole last problem without knowing the velocity. But here they actually did tell us something useful. 2 centimeters. If it gets 2 centimeters into the field, that means they've told us the radius. If that's 2 centimeters, then the radius of the circle is 2 centimeters. So now we can go to our formula, R equals mv over qb, and we can solve it for the velocity, and we know everything else now. Okay? So what would it be? It would be v is r qb over m. R qb, the field magnitude, over m. So r, I'll just write 0.02. I'm going to do this all MKS units, 0.02 meters. Q, the charge of an electron, 1.6 times 10 to the minus 19 coulombs. I'm doing it all MKS units. B, 10 to the minus 3 teslas. It was a millitesla, right? Was it a milli? Yeah, 1 millitesla. And then over m is 9.1 times 10 to the minus 31, because that's in kilograms. Yes, an electron does not weigh much. If you do that, you get that the velocity is 3.5 times 10 to the 6 meters per second. That's really fast. Okay, so one good check in physics, whenever you calculate the velocity of anything, is make sure it's less than the speed of light. Okay, it'll always, we would never give you a problem where it comes out greater than the speed of light. So in this case, it's very fast, but it is less than the speed of light, which of course is 3 times 10 to the 8 meters per second. So now you plug this into KE, just your standard formula for 1/2 mv squared, where m, again, is 9.1 times 10 to the minus 31 kilograms. V is 3.5 times 10 to the 6 meters per second, and you get 56 times 10 to the minus 19 joules. An extremely small amount of kinetic energy, but keep in mind it's just an electron. It doesn't weigh much. So even though it's going fast, this extremely small mass keeps the kinetic energy really low.